Hi everyone. In the last two videos, we saw one invariant you can use to implement sets of naturals as lists, where we used EQB to just make sure there were no duplicates when we inserted things. And we saw how to implement the various set operations that way. In these next two videos, we're going to talk about a different way to use lists to implement sets of naturals. We're going to strengthen our invariant. And what that's going to do is let us define some slightly different operations that will have different properties. Overall, the reasons why you might choose another invariant might be your code gets simpler, it's conceptually a better invariant, or most often, it's more efficient. That's the reason why you would do it. So we're going to choose one that really is ultimately about making it more efficient. I know not a big focus of the course, but this is the motivation for this other invariant. We're not going to see why or how it's more efficient. We're just going to assert that it is. You can think about that if you like, and then we'll see what the operations are. Okay, so what's the invariant? The invariant is keep your list sorted. The list should be sorted ascending. Now, not just sorted ascending in the sense of our sorting file, where it's never descending, but strictly ascending. There should never be any duplicates. So this is a stronger notion of sort than the one that we saw before in day 6. Okay, so to do that, so here's a test for it. So this is set like for these sorted nat lists. And I'm using a funny pattern notation here called as, which is a convenient way for me to say, okay, give me the first element, and then the tail of the list, L, it should also have this form, right? I've singled out the singleton case here, so there should only be lists of length at least 2 here. And then this as clause is implicitly something like this. Right, that's what it's really turning into. Right? If you don't understand that completely, you could view this code as being a little different. It's something more like this. Okay, so we could write this, or we could write, well, let me indent that better, all that. It's a little bit more code to do it this way. This might be a little clearer to you. It has the same net effect. It's exactly the same stuff. And so I'm going to leave it this way. I encourage you to play with it. Check it out. Okay. So that's his set like. Your exercises are to define some more of these list operations, but using the invariant and maintaining the invariant. So what do we mean by that? So let's look at member first. So supposing that your natsets are using here the sorted list invariant, your input is sorted ascending and there's no duplicates. Define member. Now, let's think for a second. Would the old member function work on this invariant? What do we mean by work? Will it ever return a wrong answer? Will it return a wrong true or a wrong false for this invariant? Can you use the sortedness invariant to make things more efficient when we know that L is sorted? If L is not sorted, I'm saying it's okay if you give the wrong answer. Then lastly, I give a bit of a hint. Solutions that always traverse the whole list will not receive full credit. So here I'm giving you a hint. Your member should be able to return or give up early. When? Use sortedness to figure it out. Okay. The last operation that I'm going to show here is union, and I'm going to talk about this in the next video because it's going to mean introducing a new feature from Coq. So that'll be coming right up, but you've got this exercise here, and then you'll work with union down below. Later on, I'm going to skip ahead. You're going to want to define subset, so I'll have you defining that. And then later, I ask you about set equal, but won't do it. So you're not going to be able to define subset until you've watched the explanation of union. Hopefully here, what you need to do here is clear. If you're not sure, I want to urge you to reason by examples first. Give yourself 10 minutes, come up with some concrete examples that do and don't satisfy the new invariant, and then see what your member function should do to them. If after that you're stuck, take it to Zulip. I'll see you soon.